Hello and welcome back. Let us continue our class of soil mechanics. I think this video will be the last video of the chapter 4. So we are still on this chapter, plasticity and structure of soil. So in the previous video, we have talked about all these points up to, I think, activity of soil. So in this video, we'll try these two, plasticity, the Casagrande plasticity chart, and soil structure. Okay, let's start with the plasticity chart. This chart is very important for the classification of soil using the unified classification method. So in this chapter, I think we have talked about plastic limit and liquid limit. Okay, so these two limits, they can give a lot of information about any cohesive soil. Please remember that these limits are not for cohesionless soil, not for sand or gravel, for example. These are these are used for fine soil, cohesive soil, like clay. Okay, so liquid limit and plastic limit, these two are very important in the classification of this kind of soil. Okay, so Casagrande, this researcher, in his research, he came up with what we call plasticity chart. And that plasticity chart includes an empirical A line, which is shown in this figure. So this is the plasticity chart of Casagrande, proposed by Casagrande. And the A line is this line. As you can see, this line is the A line. So what is this chart exactly? This chart is allowing you to use liquid limit. You can hear horizontal line. The horizontal axis is liquid limit, and the vertical one is plasticity index. I think you remember what is plasticity index. Sorry, I didn't include the formula here, but if you check the previous video, we have talked about all this. Okay, if you have the liquid limit and the plastic limit, you can easily get the plasticity index by doing liquid limit minus plastic limit. Okay, I hope you remember that. So this line are kind of like, if you have liquid limit and the plasticity index, you can determine, for example, what type of soil you have. Okay, now this area is cohesionless soil, no soil that doesn't have cohesion, like sand or gravel, for example. So this is the color code is here. Okay, so if we check, for example, this area, maybe it is this one, I'm not sure. Inorganic silt or high compressibility and organic clay, this area. Okay, this one is maybe this part, which is inorganic silt of medium compressibility and organic silt, this area. So each area you check, you can find out, for example, here, this plotch, within this area is an organic clay of high plasticity. Plasticity is high here, of course. Plasticity index is high. Okay, so this chart is used in the classification of soil, of fine grained soil. Okay, the line, this A line, the line help to differentiate the organic clay and silt based one. Okay, and silt, organic clay and silt based on the plasticity index and liquidity and liquid limit, as I explained. So this chart will help you to separate. It will help you to know if your soil, the soil you are dealing with, is an organic clay or silt. Okay. And the chart, as I was saying since the beginning, is used in soil classification, especially the unified soil classification system. This one is, I think, in chapter 5, the following chapter. After this video, the next video will be about soil classification. So the U line, we have another line here, as you can see. This one is the U line. Okay. This U line positioned above the A line. A line is here, U line is here. Represents the upper limit of plasticity index to liquid limit relationship. Okay. And this U line is known as relationship in the soil. The equation for this U line is given this plasticity index equal 0.9 the multiply of liquid limit minus 8. This equation is here, is written here. And this equation as well is for the A line. This one is for the U line, and this one is for the A line. Okay, I hope you understand what I mean. This chart is used to separate inorganic clay and the inorganic clay and silt, and it is used to classify soil, cohesive soil in the classification in this classification system, unified soil classification system. Okay. These two lines, A line and U line, can also be used in other way to determine the shrinkage limit of soil. When you know the plasticity index and liquid limit, of course. Okay. So how does it work exactly? This figure is explaining how to obtain it. So by using this figure, you can obtain the shrinkage limit. Okay. We are going to explain this, how it works exactly. The first step is to plot the plasticity index against the liquid limit of given soil. That will be point A. For example, this is just one example. So it means you have your soil, you try to get the plasticity index of your soil. The liquid limit first, maybe. Liquid limit and plasticity index. If you can get these two, in the previous video, we have explained how to get these two. How to get the liquidity, the liquid limit, the plastic limit, and plasticity index. So if you have the plasticity index and the liquid limit, you plot the point in, this is like just like coordinate. Okay. So if we plot our point here, point A. After that, what you do is these two lines, you project them, line A, this line A, and line U downward. Okay. And this, the projection, you project them, they will meet at certain point around here. This point is called B. Okay. This point will have coordinate of liquid limit minus 43.5 and plasticity index minus 46.4. So in the horizontal axis, it will be this, and the vertical axis will be this. This will be the coordinate of this point B. And what you have to do next is to join the point A to this point B. And in that case, when you do that, the line will cross the horizontal axis at this point C. Okay, and this point C will be the estimated shrinkage limit. This is how you got the shrinkage limit, by using this Casagrande plasticity chart. Okay, let's go to the soil structure now. The plasticity chart is, I think all the information concerning plasticity chart is okay. It's used to classify the soil to know what type of clay or silt you are dealing with, and also used in the soil classification, unified classification system. Then let's move to structure of soil structure, how different type of soil are made. We have mainly two type of soil: cohesive soil and cohesionless soil. But soil structure refers to how the soil particles are organized and influenced by factors. It's influenced by factors like particle size, shape, mineral composition, and soil water characteristics. And the soil are broadly categorized in two groups. And this is what I was saying: cohesionless soil and cohesive soil. Cohesionless soil, this means soil that doesn't have cohesion. It's like sand and gravel. These are like coarse grained soil. But cohesive soil are fine grained soil. Those soil, they have cohesion. For example, clay. Okay, that is the meaning. So mainly these soil are separate in two main groups, considering the cohesion, if they have cohesion or they don't have cohesion. Okay, each of them have different type of particle arrangement. Okay, so if we check the case of a cohesionless soil, means in case of sand and gravel, for example. So the cohesionless soil structure typically fall into two main categories. Two categories of the organization of the soil particle. It means the soil structure. We have single grain and honeycombed. Honeycombs, I'm not sure if I read it very well, but there are two types for cohesionless soil. Okay, if we consider this one, the first one, the single grain structure, that one, the feature stable particle arrangement, with each particle in contact with its neighbor. Okay, the particles are in contact with each other. This is, for example, in this case, you can see the particles are in contact with each other. So this A is when we have loose sand, for example, loose state of the soil. And this one is when it is dense. So as you can see, there are less space when it is dense. So the packing denseness can vary depending on the particle shape and size distribution and relative position, as you can see. So that will result with wide range of void ratio. And the second one, this one, honeycombed structure, that one consists of fine sand and silt forming small arcs with particle chains. It's something like this. It's maybe beautiful. And we have void here. Soil solid. Okay. As you can expect, this type of structure uh, have significant void ratio because the void are too much in this type of structure. And it can support regular static load, but they may experience substantial settlement when subjected to heavy or shock loading, as the structure can break down under such condition. Still, the structure in cohesive soil cohesionless soil is finished. Let's now talk about the case of cohesive soil. Okay, when the soil has cohesion. For example, if we take clay particle in water, clay particle in water, they have I think we have talked about this before also, the beginning in chapter, I don't know, 1 or 2. And if you put soil particle in water, initially they repel each other due to strong repulsive forces. Okay. And this allows them to remain suspended in the water, and they undergo random browning. What is this Brownian motion? Anyway, they just move in the water, being suspended, and they formed a dispersed structure with parallel particle orientation, something like this in this figure, the case A. This is when we put clay in water because there are some strong repulsive forces, so they remain in suspension in the water and they have this orientation. This is microscopic, so kind of we cannot see it, but this is what happening actually. What is happening in the clay when you put clay in water? And then when clay particle initially dispersed in water, when they come closer to each other during this random suspension, they may clump together due to electrostatic attraction. There is attraction between the particles, and then they will form flocks. Or what is this flock? Maybe flocks. Okay, these larger flocks settle under gravity, resulting in a sediment with flocculation structure. This is flocculation structure. So they touch each other, but there are kind of voids inside. And then if you add salt, if you add soil in this dispersed clay water mixture, it means when you have your clay in water mixed together and you add salt inside, the salt will affect the clay because the salt will reduce the repulsion between this clay particle. Okay, and that make the particle aggregate into into flux, and the flux will settle. The same flux are here. As you can see here, there are more attraction because of the salt added. Okay, so this form the flocculation structure also. This figure C. They are more kind of more parallel than this one. That is the main difference actually. And still with cohesive soil. In nature, it's very difficult to have clay mineral deposit, the pure clay mineral deposit. It means 100% clay mineral deposit. It's very difficult to obtain that in nature. But if you have a soil content minimum containing 50% or more particle with 0.002 millimeter size or less, can be less than that, 0.002 millimeter or less, then this soil is generally classified as clay. And we will see this classification deeply in the next chapter. Depending on the percentage of the fine in the soil, you can classify the soil as clay. So it means if your soil contains 50% or more in weight, the soil particle are 0.002 millimeter or less, then your soil is classified as clay. So there are some study using microscopes that show individual clay particles tend to aggregate into submicroscopic unit. And these submicroscopic unit are called domain. Okay, we can see it here. Domain. Microscopic. First, they are microscopic, but they aggregate together to be submicroscopic, like this. Then, but still, you cannot see them actually. You cannot see them with your eye, with naked eye. And after that, this domain, they group together again, and they form clusters. These clusters, something like that. Okay. And these clusters are visible under light microscope. And this from this cluster, when the cluster comes together, then they will form what we call peds. Example here, peds. Okay, so these peds are visible without microscope and are considered as like microstructure features, often associated with joint and fissure. Okay, so as you can see, cohesive soil exhibits a highly intricate, very difficult structure with both microstructure and macrostructure and microstructure playing significant roles. So this table is summary of all different type of structure, the clay structure we have. There are in total 5 of them. Okay, the dispersed structure, these are formed by settlement of individual clay particle, more or less parallel orientation. This is this case, for example, the A case. And the flocculation structure, This flocculation structure is formed by settlement of flocks of clay particles. These two cases are the case we are talking about here. And this domain are the aggregated or flocculated submicroscopic unit of clay particle. These are here, this domain. And clusters, domain group to form cluster can be seen under light microscope. These ones. And at last, peds. These peds, it can be seen without microscope. Okay. Obtained from this multiple cluster that aggregate together. Okay, I think that's all for this chapter. So in the next video, we will start a new chapter, chapter number 5. Okay, thank you very much. Let's finish. See you next time.